Okay, I'm going to go over the exam and uh, work the problem so you can see kind of what the correct solutions were. All right, number one, which of the equations is probably the best? Okay, so we kind of look at this. We're going to say, here we go, we recognize that this is going to be a linear approximation. So, we'll draw some, appropriate line, through here or something like that. Okay, what we see is that this is going to have a negative slope and a positive y-intercept, right? Plus b, and that's going to have a negative m. And so we just look over here and see what, and this has negative m. This is the only one right here, b, that has a negative slope and a positive intercept. Okay, question number 2 is asking us to give a linear approximation of this function. So when I think linear approximation, and here's a function that is nonlinear, I'm instantly going to go in my mind to the um, oh, I just forgot the Taylor series. Yes, I was going to say Fourier, but it's not Fourier; it's the Taylor series. So what we're going to say here is the x of t, then, and this is going to be around 0.5. It's going to be x of 0.5 plus the derivative of x with respect to t evaluated at x equals 0.5. That's going to be t, oh, excuse me, that'll be a t equals 0.5 and t minus 0.5. Now, if I were doing the full or multiple terms, then this would be 1 over 2 factorial d dx dt d squared x dt squared t minus 0.5 squared, etc., etc. But we're not, right? This is only linear. So this is what we're going to be working with, right? So that is going to be 1/2 0.5 cubed, right? That's this x of t plus 3/2 0.5 squared t minus 0.5. I just did that in my head. The derivative here, x dot, is going to be 3/2 t squared, right? So this gives us then 0.0625 plus 0.375 t minus 0.1875. Okay. Then our x of t is going to be 0.375 t minus 0.125. Okay, we could also represent that as 3/8 t minus 1/8. Just depends on how you did that. Into shape. There. That is the answer for number 2. What is the Laplace transform? Here for this particular equation. This is pretty straightforward. Looking at table, I'll show you this table. You know what? I'm going to decrease that. Well, I'll keep it big. Table, not just me, right bigger. 2.2.1. We're looking at case number 8. Okay. Says that if x of s is equal to b over s squared plus b squared, then x of t is going to be equal to sine of bt. Excuse me. All right. So I'm looking now at this. There's my s squared. Then I want to be able to say then that b equals 2. If b equals 2, then the denominator is going to be s squared plus b squared. Okay, so from there, going back to here, our original equation, I say x of s is going to be 15 over 2 b over s squared plus b squared. Okay. Which tells us that our x of t, then 15 over 2 sine of bt. We can plug back in for our b. X of t is going to be 15 halves sine of 2t. Okay, is 7.5 sine of 2t. Either one of those would have been just fine. Either one of those two forms. All right. Here we go, number 4. Is this stable over time? Okay, so what we're looking at is, as time goes on, does this function f of t grow out of control, or does it settle down? And so we'll take a look at these. So 3 over 16 is steady. Okay. 2 over t plus 1. So if t was -1, this would be infinity, but t never goes into the past, right? So since t is always going to be greater than or equal to 0, then this one is also steady in that it approaches 0. Okay. Since we have a negative t here, and since t does not go to negative infinity, it's always greater than or equal to 0, then this also is going to approach 0. So f of infinity then is a constant. It is stable, and that's going to be 3/16. So the answer is yes, it is stable, and some sort of an explanation, about some sort of an explanation, kind of like this stuff would be the explain that I'm looking for. Okay. All right, next, let's look at problem 5. What is the equation of motion, x of t? Okay, so what we're trying to solve here is x of t. We've got our a second order ordinary differential equation. We've got zeros here. There's a number of ways to solve this. I suggest that we do it using table 2.3.2. Right, that's the way that we've most talked about it in class. X double dot plus 4 x dot plus 4x equals 5.6. And what I did is I just divided 5 by everything. The reason is that I want here a coefficient of 1 in front so that it matches this table, table 2.3.2. Okay, and so we look, we say here that a equals 4, b equals 4, that tells us that this is case 2, which is when a squared equals 4b. Okay, so this is case 2. All right, so the form there, or the solution is in this form: x of t is equal to c1 plus c2t e to the s1 t plus c over b. Let's see, so we got a equals b. Oh yeah, we'll add one more thing here, and then c equals 5.6. All right, we're going to need that. What we see here, and I'm going to draw a little arrow, is that that is an S, which means we're going to need the characteristic equation. And we can develop that simply from here, right? Our characteristic equation, we understand, is this s squared plus 4s plus 4. Okay, we'll say equal to 0, and that's how we'll solve for our roots. The way we did that, as we understand, is we just take an x double prime, turn it into an s squared, an x prime, turn it into an s, and then an x will just turn it into nothing. And this is our characteristic equation. And what this gives us, then we'll solve that. This is going to be s equals -2, right? And -2, so this is double. I did that simply by saying that this is the same as s plus 2 squared equals 0, and just solve for s there. All right, so our s then we know is -2. So this s is going to be -2 right there. C over b, that's going to be 5.6 over 4 from here, right? That's our c, that's our b. And then we just need to solve for these coefficients. Okay, so let's come back to our original formula. X of t is going to be c1 plus c2t e to the -2t plus 1.4. All right, we know the x of 0 is 0, so we'll say x of 0 is going to be c1 plus t0 times 1 plus 1.4, which gives us that c1 is going to be -1.4. Okay, we can take the derivative. We'll say x prime of t. Okay, now we're going to need to use the chain rule, right? We've got a ct on the inside and then a -2 t here. And so that would be simply c2 times e to the -2t minus 2 c1 plus c2t e to the -2t, right? So it was, I hope you understand how to do the chain rule. I'm not going to go into detail there. That's a calculus that you should know. X of 0 is 0, or x prime of 0 is 0. So that's going to be c2 minus 2 c1 plus 0 times 1, which tells us that c2 then is going to be -2.8. And plugging this back into our equation, x of t is going to be -1.4 minus 2.8 t e to the -2t plus 1.4. Okay, there's a number of ways that you could have represented it. It would also be negative 7/5 minus 14/5, like that, e to the negative 2t plus 7/5. You could have also kind of factored things out. 7/5, 1 minus 1 plus 2t e to the negative 2t, like that. That would have been another way that you could have done it. Okay. There's an alternate way that you can solve this x of t. Some of you did that, and there you go. That's the x of t, and I will go ahead and work that one as well. I'm going to erase what I've got here, just so that you don't get confused. Delete. All right, so here's our equation. Since we see that there are 0 initial conditions, we should say, aha, exclamation point. Table 2.3.1 is specifically for equations with 0 initial conditions. Okay, so we look at table 2.3.1, and you're welcome to pull that up, from your book or from whatever. But case 3, I'll show you. So case 3 from table 2.3.1 is this. It says if your ODE plus 2a x dot plus a squared x equals mus of t, then the form is, or then it says, then the roots are s equals negative a and negative a, and x of t equals m over a squared 1 minus at plus 1 e to the negative at. Okay? So let's ask ourselves, can we put this equation in this form? If we say, well, let's see, we've got to have a 1 out here, so we'll go ahead and divide through like we did last time. X double prime plus 4 x dot plus 4x equals 1.4, or excuse me, equals 5.6. Okay, so here, if we say that a equals 2 and m equals 5.6, okay, let's take a look at that. Okay, if a equals 2, then 2a is going to be 4, okay, check, that is correct. And then a squared should be equal to 4, check. All right, m here is 5.6. Yes, that is correct. And we know that this u s of t, this a unit step function, is 1, number 1 for t is greater than or equal to 0. Okay, and so we are in that realm where t is always going to be greater than 0 because it's a function of time. So we are gonna meet that form. So we'll go and do that using our a's, using our a and m's and all of that stuff. X of t, let's see, m 5.6 over 4, 1 minus 2t plus 1 e to the negative 2t. Okay, and this is 1.4 times 1 minus 2t plus 1 e to the negative 2t. And if you were to rewind the video, you would see that this is the same equation that we obtained solving it the other way. Okay, that's that. Problem 6. Solve for the total response and find the steady state and the transient, if any. There were a number of ways to do this. Let's see. 1, 2, 3. There's 3 different ways. I'll show you 2 of them. Let's see, table, excuse me. Using table 2.3.2. Okay. This is, oh man, we love this. This is the first order differential equation. So this is pretty straightforward. We've got to have this coefficient though in the front to be equal to 1. So let's go ahead and do that. X dot plus 5 halves equals 5/4. Let's see, x dot plus 5/2, 5/2 x equals 5/4. Okay, and looking at table 2.3.2, there's only one case for the first order, and that, as we see here, this is a equals 5 halves, and then b equals 5/4. Okay, for a first order equation, that's always going to be of this form: x of t is going to be b over a plus c e to the negative a t. Okay, x of t is going to be b over a. So this is going to be 1/2. Just using our a and b from up here, plus c e to the negative 2.5 t. All right, that's a right here, 2.5 x of t. And we have an initial condition that says x0 is negative 3 halves. So we can solve for that here. Negative 3 halves equal 1/2 plus c times 1. Move this 1/2 over, so we're going to say c is going to be negative 2, which tells us that our x of t is going to be 1/2 minus 2e to the negative 2.5 t. There we go, and so that is the equation for that. There is another way to do it using some other tables, and I'll go ahead and work that for you quickly. I'll need to do that here by erasing this. Erase, erase, erase. Okay, so the other way that you could have done this is kind of 2 steps. Oh yeah, hang on. I was supposed to look at the transient versus steady state. Let's see, let me pull that back up. This was, we'd said x of t 1/2 minus 2 e to the negative 2.5 t. Right, we can see that this is a constant, so that's going to be our steady state. And then this is decays as you see that this goes to 0 as t goes to infinity. Then this is going to be our transient response here. Transient response right here, and then this is our steady state. All right. Let me show you the other the other solution that you can follow to get to this answer. And this is to, like I said, to do it in 2 parts. Now, when we look at this, this is neither a 0 initial conditions or a 0 force or a 0 input. So what we have is kind of 2 things combined, and I'll draw them over here so we can see, and that is that we have a free and a forced solution, okay? And what we're going to do is just solve for these both and then just add them together, okay? So the free response, now when I say free response and forced response, notice that this is different than the steady state and the transient, as you'll see. Okay, free and forced is not the same. So the free response, we're going to solve this for x dot plus 10x equals 0 with x of 0 equal to negative 3/2. And over here, we're going to solve for the forced for x dot plus 10x, let me fix my handwriting, 4x dot plus 10x equals 5, x of 0 equals 0, okay? So we're going to get a free response on this side, we're going to get a forced response over on this side, and then we'll just add the 2 together, okay? Using table 2.3.2, okay, the form here, we've got A is 5/2 and B is going to be 0. Remember, we need coefficient of 1 here, so 10/4 is the same here as 5/2. And once we substitute in then and use the initial condition of negative 3/2, we're going to find that C is negative 3/2, negative 1.5, and that'll give us that x of t is going to be equal to negative 1.5 e to the negative 2.5. Okay, so that is our free response. Okay, our forced response we can solve using table 2.3.1. Table 2.3.1, it's going to be case 1, and that says that if our differential equation is like this, plus ax equals mu t, that step function there, then the form is going to be x of t equals m over a times 1 minus e to the negative at, okay? And so using this, we'll say that a equals 5/2, and then m equals 5/4, right? Oh, excuse me, I'll put this over here. And m equals 5/4, and that gives us this equation f of t. Now remember, this is just the forced response. 5/4 divided by 5/2 1 minus e to the negative 5 over 2t. Okay, so that is our forced response. Well, let's simplify that. 1/2 1 minus e to the negative 2.5t. Okay, and so we need to add to get our total solution is that we're going to add our free. Now, this is a much longer way, but it is a way, is to divide it up into the free and forced, and then add them together. So when we add these together, this minus 1.5 e to the negative 2.5 and this 1/2, 1 plus et cetera, we end up with this. Okay, this will say our x of t is going to be negative 1.5 e to the negative 2.5t plus, now this, plus 1/2 minus 1/2 e to the negative 2.5t. Okay, notice we have a minus 1.5 and a minus 0.5 over here, again to this exponent, so we can simplify this to 1/2 minus 2e to the negative 2.5t. Okay, and that would be the solution. And you see that this is exactly the one that we calculated before. Again, looking at the steady state and the transient response, we'll see that this is the steady state and that this is the transient response. Steady state response right here. And we can see that this is not the same as the forced and the free. We look back here at this free response. This free response is only transient, whereas the forced response is partly steady state and partly transient. Okay. Now let's look at number 7. Now this was the one that I didn't include, or that I gave you the full, I gave you this full 5 points for. But so here's the way that you do this, just so you know, kind of for future reference for other exams. Okay, we're going to need to kind of see what's going on here. So this is about 875. This final FEP value is about 375. Okay. And so that's the total change from here to here is about 500 units, whatever those units are. Okay. Now, we've got the change here. It doesn't happen right at 4.35. Happens out here. I kind of eyeballed it. I'll do this in red so it shows up a little bit better. 4.404. Numbers around there were okay. And what we want to see is now this tau is going to be, or excuse me, the time constant is going to be 63.2%. It's what time, or how long does it take to get from this time, which is where it started, out to some place around here where it's going to be 62.3% of the way there. Okay, so the whole distance there is 500. 316. Come down, if we come, whoops, let me try a different color. If we come down 316 to about 559, let's see, 559, something like that, to about right there, right? So the way I got that is I said that 500 times 0.632, right? That's this 316. there. So 875 down 316 gives us that point. Okay, and so our time constant is going to be this time minus that time. I estimated that to be, just again eyeballing it with my pencil, 4.418. Okay, and so then the time constant tau is going to be 4.418 minus 4.404, which here is going to be 0.014 seconds. Okay, that's going to be our time constant. And this is going to vary a little bit just based on how you're eyeballing these different values over here. But that's roughly going to be what that is. You can also look and see, if you come out four time constants, 1, 2, 3, 4, then you're down around this range where it's almost leveled off there at this 375 value. Okay, this was maybe a little bit more beyond what we've talked about in class, and so that's why I gave everyone full credit for this problem, which means that if you did get partial credit, and I gave partial credit for identifying certain things, these values and these points and that sort of thing, then that would be just bonus for you. All right. So number 8. This question is, what is the time constant with the following behavior? How long will it take to reach steady state? Okay, what we look at here is that. Okay, it's the exponent of the coefficient, and so it's always going to be the inverse of that. Okay, essentially whatever makes this exponent to be -1. Okay, so then tau, and then this is just from eyeballing it, that's just going to be 1/2. Okay, so there wasn't really any math to do, it was just noticing. Okay, it's the time constant is whatever makes this exponent of the transient component, whatever makes the exponent to be 1. Essentially 1 over whatever's there. And then when we say how long will it take to reach steady state, that's essentially code for multiply the time constant by 4. And that would be 4 times 1/2 equals 2 seconds. So it would take 2 seconds to reach steady state. Time constant right there, 2 seconds to reach steady state. Okay. Problem number 9. It asks us here for to find out how many teeth. Now, I hope nobody sat down and actually counted how many teeth were on these. That was not my intent in producing this drawing for you. Okay, but we are given 2 inertias here, and then we have an effective inertia. Okay, my hope was you'd say, wow, that's big. If you just sum up the two, 3 kilograms and then 21.75, that there's a big difference. 6 would be just double. So I hope you can see that there's going to be something that's going to be spinning pretty fast right here. So we're going to do this, as it says here, from the perspective of shaft number 1. Okay, so this is key. So this is the equivalent inertia from the perspective of shaft number 1. What that means is when everything is considered to be spinning at this angular velocity, then it behaves as if this is the moment of inertia. Okay. The way that we do this, first we're going to need an equivalent inertia. We say the kinetic energy is 1/2 I1 omega 1 squared plus 1/2 I2 omega 2 squared. Okay. Now we know that there we know that there is a gear ratio, but we don't know exactly what it is. But we can say, and here's kind of that equation already, we can say that our omega 2 is going to be our omega 1 divided by n. Okay, so when we put that now into this kinetic energy equation, this is going to be 1/2 I1 omega 1 squared plus 1/2 I2 omega 1 squared over n squared. Notice I had to square the denominator as well. Okay, so again, putting this in that form that we're looking for with omega 1, 1/2 something times omega 1 squared, and that something is going to be I1 plus I2 over n. Okay, and that's going to be the kinetic energy. Okay, so from here, we are going to find that this is our effective moment of inertia. This is given, so we're not going to go far beyond that, right? So this is going to be 21.75, which is given in the problem statement, equals I, we know that this is 3, that was given, plus 3, which is I2, over n squared. Okay, solving this equation gives us that n is going to be 0.4. Okay, then we can come back up actually to this equation. N equals omega 1 over omega 2. We made a point in class to say that this is the reverse of the numbers, right? So this is going to be n2 over n1, which is the number of the teeth, okay? So if we say 0.4 equals n2 divided by 30, 30 was the number of teeth which was given, we'll find that n2 equals 12, okay, and that was the answer. There are 12 teeth on the gear attached to this shaft, and there are 30 teeth attached to the gear on this shaft. What that does is it makes W2 spin way faster, and so that's where this seemingly heavy moment of inertia comes from. So that's the answer. So there's 2 number 10s. I'm not sure which one you did. I'm going to go through and solve these both. For this one, for this number 10, the first one, or for number 10 and number 11. I'm sorry. I keep saying there's 2 number 10s, but there's not. For number 10, there was a lot of ways to solve it. Fundamentally, here's the things that you needed to know. You needed to recognize that the tension here is 9 pounds, okay? Now, I'm not yet putting force or mass right here. I uploaded a video that talked about pound mass and pound force, and I would encourage you to go see that there on our Moodle page if you have any questions. So we need to know that tension is going to be 9 pounds. And the way that we're going to solve this is, well, we've got 2 unknowns, don't we? So those 2 unknowns are this x double dot, if we're talking about the acceleration of this mass, or it's going to be this omega dot if we're talking about the acceleration of this spool. Now, these are related, so that's one unknown, either this x double dot or the omega double dot. Excuse me. The other unknown is the mass of the spool. Okay, what is that? All right. So the way that we need to do this, we've got two unknowns. We're going to need two equations. All right. And so those two equations are going to come from a number of different places. Okay. I'm going to change colors again. Maybe go a little bit smaller just so I can write smaller. One of the places that you can get one of the equations is to draw a free body diagram of the mass itself, right? With you got the tension coming up and you've got the weight going down, okay? And to some of the forces, F equals ma. Mx double dot is going to be equal to the sum of all the forces on there. All right. Now, another place, and we'll come back and we'll solve that here. Another place that you can get an equation is just to look at the spool. Okay. And the spool is going to have a weight and a normal force and this thing out here, which is going to be pulling down, right? And here it would be sum of all the forces in X. Here it would be the sum of all the moments, right? Or so it would be I omega dot equals m, right? Which is, or sum of all m, which is the rotational equivalent here of Newton's second law. Okay. A third place that you could get an equation is to draw this as your system. Okay. If this is your system, you now have gravity pulling down here on the weight. You've got the gravity pulling down on the spool, through its center of mass. And you've got the normal force pushing back up. Normal force and then the weight of the spool. Here, this is the weight of the m for the mass right there, okay? And you can solve this in two different ways. You could say m, the effective mass times this x double dot is the sum of all these forces, okay? Or you could say the effective inertia of this combined system times this rotational acceleration equals m. Okay. Now, here's four different ways that you can get two equations to solve for these two unknowns. But there's one thing that's important to remember, and that is that these two equations are essentially the same. So if you were to try to use just these two equations to solve for your two unknowns, you wouldn't be able to. You'd end up with 0 equals 0, and it would be undefined. Okay, so what you need to solve this is either solve one of these two, or excuse me. Well, here I'll just do this. Right. So if this is method 1. This is method 2. This is method 3, and this is method 4. Okay, so the options that you have are to solve this. It can be 1 and 2. It can be 1 and 3. It can be 1 and 4. It can be 2 and 3. It can be 2 and 4. Okay. So, let me see. How long would it take for me to, you know, it wouldn't be, I'll do all of these. I'll do all of these. It wouldn't be too bad. If you've got room, just make sure that you make a lot of room if you're writing these things down. Okay. Let's take a look at this. Okay. We're gonna just generate this equation and look at all of these. So we know that this is a 9-pound tension. Okay. So I can say I know that this is a 9-pound force. Okay. With a tension, tension is always going to be a force. So that's going to be 9-pound force. Okay. Now we have the weight though of this, and so that is going to be, what is it? 15? Yeah, 15 pound. There's a couple ways to do this. I would suggest saying 15-pound force. Okay, there's another way you could do that, and you could say, and I'll just kind of do this. I'll just do this up here, maybe a little bit smaller. And that would be the weight is the mass times gravity. Okay, and if you say the weight now is 15-pound mass times 32.2 feet per second squared, then that would be, I don't even know what number that would be. Let's see, 15 times 2.2, 483. So it'd be 483 pound mass feet over second squared. Okay, but we need to not put it in pound mass feet over second squared, because the units of weight here is going to be a force, right? Force versus a force. And so we're going to say that 1 pound force is the same as 32.2 pound mass feet per second squared. Okay, 483 divided by 32.2 is going to be 15-pound force. Okay, so I would suggest just saying, 15 pounds, that's a force, and then just going with it like that. Okay. Anyway, 9 and 15. So we're summing the forces here. We have the mass. The mass now, it's not 15-pound force. The mass is 15-pound mass. Okay. The x dot is unknown. And that is going to be the sum of all the forces. That is going to be 6-pound force. So the question is, what do I want? Do I want it to be up or down? How do I want to define that? We'll go ahead and call, for me, you can do it any way you want. We'll go ahead and define kind of this as the positive x direction, just because we know that's the way that this weight is going. Okay. And so what we have here is x double dot is going to be 6-pound force divided by 15-pound mass. Okay. Now we can't just drop all that. We actually need to make this conversion. And that is going to be here times, we say 1 pound force. Oh, let's see here. What do I want? Yeah, so we want to cancel all of those out. So 1 pound force is going to be 32.2 pound mass feet per second squared, all right? Which tells us then that our x double dot is going to be 12.88 feet per second squared, okay? That is going to be our vertical acceleration of that mass. Now we could very easily, and this is kind of part of the lanyard, we could very easily say, oh, wait a minute, if the mass, where's my picture? If the mass is moving that fast, then that spool, we can easily calculate what that angular acceleration is. And that would be simply the angular acceleration is going to be linear acceleration divided by this radius r. In other words, 12.88 feet per second squared and divided by 1.6 feet, 1.6 feet, which is 8.0505 radians, okay? So that is actually one of our unknowns. So here we've got one equation, one unknown, and we're able to solve for it. Okay, so if that was one of the equations that you solved, great. We're you're halfway there. You just need one more equation, one unknown. It can be equation 2, it can be method or this equation number 3 or number 4 over here. Okay, so if we did this where we've got equation, we'll do this kind of over here, where the spool is our system, then yes, we got weight and normal force. That's all going to cancel out, or that doesn't matter. I mean, we're going to do the moment here around, around that pin, moment of O or whatever that is. And so that those two forces, the weight and the normal, is not going to come into play. But we do have this one, okay? And so this force here is going to be 9 pound force. Okay, it's not going to be the 6 that comes from here. It's not going to be the 15 pounds. What the spool knows is that that string is pulling, and it's a 9 pound force with which it's pulling. That's all it knows. The spool does not have eyes, can't see beyond its touch. Okay, so this is the equation here. Let me get to where I lost my spot. Okay, the formula for this moment of inertia is going to be 1. Oh, let me try. That's going to be 1/2 mr squared. Now that's going to be ms. That's the mass of the spool. Okay, times omega dot is going to be equal to the 9 pound force. 9 pound force times the distance, 1.6 feet. Okay, now we need to be a little bit careful because this is a force and this is going to be a mass, and so we need to just make sure that we get our units correct and do any conversion that we need. Okay, I'll go one more step and we'll just kind of fill in this stuff. If we were to solve for yeah, I'll do this. I'll do this. So that way you'll be free. So this is going to be your m of your spool times omega dot. Both of these are our unknowns. Okay, and that's why I'm putting this over here. If you want to use the omega dot that you found from here, or mass of the spool that you can find somewhere else, then you can do that. So this is going to be flexible. So if we just want to solve for this mass times the angular acceleration, This is going to be, well, yeah, I'll show you. So this is the 14.4 pound force feet. We need to kind of keep an eye on that. Okay, so divide all this out. That's going to be 14.4 pounds force feet divided by 1.28 feet squared. That's what this is. R squared divided by 2. That's the 1.28 feet squared. Okay, notice that we have a pound force over here, but we really want this to be a pound mass. Okay, all this is going to give us is a per second squared. So let's go ahead and make this conversion. We want to kind of get a pound mass in here instead of a pound force. Okay, and so we're going to multiply. We want to get rid of pound force. So 1 pound force is going to be 32.2 pound mass feet per second squared. Okay, and so let's just kind of take a look at the unit. So here we have ms omega dot equals 362.62.25. Let's see here. Pound force cancels out. Feet and feet, it makes feet squared, cancels that out. Okay, so what we're left with is pound mass per second squared, which I really like, because the pound mass is going to be here, the mass, and then the per second squared, that's going to be this angular acceleration. Okay, so this is kind of that second equation. Now, if we wanted to just kind of stop here, we say, oh, we've got an omega dot, we've got an angular acceleration. If we were to plug that in right here, what we would find, if we just brought these two together, what we would find is that our ms equals 45.000 pound mass, 45 pounds. Okay, the school is 45 pounds. Okay, but that's not the only way, right? So you just need two equations, two unknowns. So let's take a look at this. So let's do way number 3. Way number 3, okay? And that is this. So an effective mass times is x double dot equals the sum of all the forces, okay? We'll do this, the sum of all the forces in y. We see that these two kind of cancel themselves out. And then we've got this one. Our effective mass, x double dot, equals, we'll call this the weight of the spool, excuse me, in that direction. So it's the weight of the spool minus the normal force minus this weight here of the mass, which is, as we know, 15 pound force. Again, check out that video. You'll be able to see that it's, if you're looking for a mass, it's 15 pounds mass. If the equation calls for a force, it's 15 pounds force. Okay, that's actually kind of the easy thing about the forces, or about the U.S. units. Okay, so we've got kind of a question mark here, and that is, well, what is this? What is this going to be? Oh yeah, I'll show you. So we see that this normal force and the weight kind of cancel themselves out. So our equation simplifies to, I'll put this here, me x double dot, or x, yeah, equals negative 15-pound force. Wait a minute. No, hang on. This should be a positive because I'm saying positive x is downward. Positive x, positive x. There we go. Okay. That's going to give us a positive force downward. Now, yeah, this effective mass, we need to get that. I'm going to draw an equation up here so you can see this. So the way that we're going to do this is using our kinetic energy formula. Kinetic energy is 1/2 I omega squared plus 1/2 m of the weight x dot squared. Okay. Now, if you wanted to, I mean, for the full kinetic energy equation, you could even include some other terms like, plus 1/2 the mass of the spool times its x double dot of the spool, but the spool isn't moving vertically. It's only spinning, right? So in this case, this term would be 0. If you were to also consider like some rotation of the little weight itself, it's not rotating. So that would all be 0. So there's no way around it. This is the kinetic energy formula, okay? And so if we're solving this version, then we're going to need to come up with an effective mass, okay? And the way that we do that, we would say, well, this omega is going to be simply x dot over this radius, okay? So then our kinetic energy, 1/2 I over r squared plus this mass of the weight, x squared, that's our equivalent mass, okay? So, we can maybe expand this a little bit more before we plug it in here. The equivalent mass, need our handwriting. The equivalent mass is I over r squared plus the mass of the weight, okay? And we know that this is 15-pound mass, okay? Now we can look here at this I. That's going to be the moment of inertia of the spool itself, okay? And so that would be this I of the spool is going to be 1/2 m of the spool r squared, okay? Notice how there's r squared here in the numerator and an r squared in the denominator. We see that our effective mass is going to be, let's see, 1/2. So it's going to be the mass of the spool divided by 2 plus 15-pound mass, okay? We can now, we'll put that into here. The spool mass over 2 plus 15-pound mass times x double dot equals 15-pound force, okay? These same two unknowns, we've got an x dot, we've got a mass of the spool. We'll go and stop there. You can use this equation plus either of these others. Let me see. You can use this equation with either of these, either with that one or with this one, and you'd be able to solve, again, for the mass of 45 pounds and for the omega dot, which is that Lagrange, okay? Yeah, what this is asking for is this omega dot. Okay, now the fourth equation that you can choose from is going to be this one. Okay, and that is IE, the effective inertia, M. Okay, now we're going to do the moment of inertia around this point here, kind of around the 0. So we need an effective inertia. So we will come back up to this equation. Okay. We kind of go off in a different direction. We would say that x dot is going to be omega times r. X dot squared then is going to be omega squared r squared. Okay. So now we look at our kinetic energy equation. Kinetic energy equals 1/2. Let's see, we can kind of factor this all out. I plus mass of the weight r squared. Okay. Times omega squared. Okay, so we see, aha, this is in that form, so we know that our effective inertia is that right there. Okay, so we can go ahead and come on down here and plug this in, right? I don't know, I'll keep this in blue. All right, so our effective inertia, I plus m, the mass of the weight, we know what that is, r squared. I'm about to plug it in. So we know what our inertia equation is. Again, this is just a spool, not the whole everything. Okay, the inertia of the spool is 1/2 the mass of the spool times r squared. Okay, so then this whole equation then is 1/2 the mass of the spool, r squared, plus the mass of the weight, r squared, times angular acceleration equals m. 1/2 the mass of the spool, it's unknown. The radius here is 1.6 feet squared plus 15-pound mass times 1.6 feet squared times omega dot. And that is to find the moment. So if we look at this, the moment has to do not with the 9, but with this 15. Okay, if we say that this is our system, then the external force of gravity is just the force on the weight. Really, it's the force on the weight plus the weight of the spool and that normal force. But we know that these two cancel out. Okay, so it's not the 9, it's not the 6, but it's this 15. And so the moment then is that force, which is the 15 pounds force, and then the lever arm right here. We can then say this is going to be 15-pound force times that lever arm is 1.6 feet. Okay, and then there's some simplification that we can do in here. I'll go ahead and stop there. I just wanted you to be able to see kind of how this process worked. Here's an equation. There's only two unknowns. The only two unknowns is this mass of the spool and this angular acceleration, and you can just combine that however you'd like. With that equation, you can use that equation with this equation. You can use this equation with this equation, okay? You cannot use this equation with this equation, okay? if you took these two and used them together, what you'd end up with is 0 equals 0, and you wouldn't be able to get to a solution. There are a number of you who actually did use these two equations and did come up with a solution, and that's because you either intentionally or accidentally made some mathematical mistakes, so you did not end up with 0 equals 0. Again, I've done 1, 2, 3, 4. Here are the different combinations that you can do of equations in order to get the unknown. Okay. Final answer in every case is 45 pounds and an angular acceleration here of this 8.05 radians per second squared. Okay. Problem 11. This is an oscillating pendulum. We are given this force, horizontal force. We know our length, we know our mass, okay, and we know our initial conditions. The equation that we're going to need to solve is this one. It's going to be I omega dot equals m. Okay, and so we need to find out what the different components are of this. Now, there's a couple ways you could have started. I would not suggest that you consider these, or to consider the middle of the particle as your origin, because in that case there is no movement with respect to the mass itself, and all you have is a gradual oscillatory rotation in the wind. Okay, and so that is a little. I'm not gonna solve that way. That's really complicated and not really the wise thing to do, especially since we have, if we say this is our origin, we have an equation for the moment of inertia. It's the very first one on the list that's there on the equation sheet. Okay, and that is that for a pendulum moving, for a mass moving around, then the moment of inertia is simply mr squared. Okay, in this case it's going to be ml squared. Since we know all of these values, then that is simply going to be 0.726. Right? Since we now have I, the question is here a little bit about the moments. Okay. Now, if we say that this is our origin, then there's a couple of moments. Okay. If we say this is our origin, the mass, there are not going to be any moments, and then we'd need to do some kind of rotational equation, but then also have the some of the forces in all the different directions and x and y acceleration. That's not the way that you'd want to do this if you knew how to do it this way. So we've got this weight. Okay, this is mass times gravity. We could calculate what that is. Okay, but what we want is the moment. Okay, the moment is going to be the force times the lever arm. Okay, there's a number of different ways that you could have calculated this. It's really all the same. I'll do this one. This angle is also theta. And so the lever arm here, which is, again, the shortest distance to the vector of that force, is L sine theta. Okay. So mgl sine theta. That is the moment about this origin due to the weight of that pendulum. And again, theta is going to be constantly changing. Okay, but we also need to add this other term related to this force of the wind. Okay, and so I could probably do this. Maybe I'll make it a little bit bigger so you can see. So okay, here's the force, and we know that this is 3 newtons right here. And what we want is I guess I can make it smaller. What we want is this shortest distance, the lever arm. Okay, so if I just kind of extend that out, then we would see the lever arm here, which is this, would be L cosine of theta. Okay, so we have this term for the weight of the pendulum, and then we have FB L cosine theta, which is due to the wind. Okay, again, there's multiple ways to divide these up into the angles, but if you do it correctly, you're always going to end up with MGL sine theta, FBL cosine theta. Okay, and so that is the equation that you're going to want to use. So, maybe before I put in this 0.726, I'll do it kind of numerically for a little bit so you can see. ML squared, that's the I, omega dot, is going to be equal to mgl sine theta plus FB. What's the B for? Oh yeah, breeze. There you go. The breeze force. FBL cosine theta. Okay. We can cancel out one of these L's. Okay. And I'm going to go ahead and turn this into a double dot, or a theta double dot. Okay, so this is M theta double dot. That'll make it a little bit more familiar. Equals mg sine theta plus f b cosine theta. Right? Now we need to use our small angle approximation, which is, for small angles, the sine of theta equals theta, and the cosine of theta equals 1. Okay, using that, m theta double dot equals mg theta plus fb. Hang on, I think I missed my right-hand rule over here somewhere. Yeah, that should be a minus mgl sine theta minus mgl sine theta minus here minus there. Yeah, sorry about that. At least I caught it before I got to the end. Okay, here's this equation, and this looks very familiar, doesn't it? This is a second order differential equation. We can put this in, oops, I got to put it out right here. We can put this in the standard form, okay? And that is, look at this. I'll show you both steps. Mg theta dot equals plus mg theta equals this breeze force. Okay, to use the equations in the table, table 2.3.2, we're going to need to make sure that this has a coefficient of 1, that first term, that second derivative. And so we'll just divide everything now by ml. Theta double dot plus g over L, since the m's cancel, theta equals FB. If you'd like to make it a little bit clearer, we could even say theta double dot plus 0 theta dot plus g over L theta equals this breeze force. Okay. Now, if we look now at table 2.3.2, this is going to be case 3. Okay, case 3, where a equals 0, b is going to be g over L. Oops. FB over ML, FB over ML, and then here we go, our M equals AB, no, excuse me, we call this a C. Then our C equals FB over ML, okay? And we those numbers, okay? Equals 0. Okay. So we can simply put this into the form that's given here for case 3. I'll go and put in these numbers right here. B, so G over L is going to be 4.4545 1 over second squared. C is going to be 0.90909 1 over second squared. Okay. From the table, we can say that our frequency, our radian frequency, which is this lagniappe here, is going to be the square root of B, which is the square root of G over L. So our omega here is 2.111 radians per second, right? Or rad per second. Okay, that's one of the things that you're going to need. It's something that you kind of get along the way that you have to solve, just like the other one for problem number 10. And so the equation here, again using case 3, theta of t is going to be C1 sine of omega t, 2.111 t plus C2 times the cosine of 2.111 t plus this C over B term, which is 0.2041. Okay. Our kind of running off the page here, but that's because I'm writing kind of big. I'll keep going. We know that theta of 0 equals 0. Sine of 0 is 0. 0 plus cosine of 0 is 1. C2 plus 0.2041. Okay, so our C2 is going to be negative 0.2041. Okay, our theta dot of t, we know is going to be um, 2.111 C1 times the cosine of 2.111 t minus 2.111 C2 times the sine of 2.111 t. Okay, we know that this is 1.5 radians per second, which was given here in the problem statement. And so at t equals 0, 2.111 times C1 times 1 minus 2.111 C2 times 0. Okay, solving this, C1 is going to be 0.7106. So we can plug these back in. Theta of t, 0.7106, sine of 2.111t, minus 0.2041 times the cosine of 2.111t plus 0.2041. 2041. Okay, so this is the equation. We can see that this is the radian frequency at 2.111, and I would need you to identify that in order to get the points as the radian frequency, to get a point to the lagniappe. And there's an interesting thing here, that I guess is, I mean, this wasn't part of the problem, but is interesting to notice. You've got a constant term here, and you got this sine and cosine stuff that's oscillatory, okay? So without any wind, you've got oscillation around the theta equals 0 term. But because there's wind, and now you've got oscillation around a different point, that is theta, is 0.2041 radians. All right, well, that is the exam. Thank you very much.